So in the NIPS, this is a top place where a human can write the paper. So I think it is not there yet. So NIPS 2019, NIPS 2019. Google. So this is the publication of the NIPS, NIPS in 2019. Still there, more than 7 keyword, graph, and graph. So graph is theoretically very strong in the representation of the information. So how do you make your graph strong? Then this is what the Google doing. Google spend their whole energy on how do you make your graph stronger and how do you make your graph representation efficient. Okay, so graph is very close to the industry, and at Google and Facebook, they spend their whole energy into make a graph that's more close to the theoretical level. Share. So I assume you know about the very basic of the graph. So since some of you may not clearly understand what the graph is, so I'm going to start with the very basic step, and we're going to move on what it is. So graph is vertex and edges. Node is vertex. What they're connecting them is an edge. Graph is one of the unifying theme of the computer science. Graph is G, consists of vertex and edges. Okay. And for example, road network. When you want to do navigation. So in a modeling network, when you are modeling road network, the vertices may represent the cities and junctions. Where should I make a left turn or a right turn or go straight? We call the junction. In a node, this is my node, vertex. This link is my edge. Okay, so the same thing happened in road network. The vertices represent the city's junction, and what they connected, the road, with what we know, is an edge. Something like Stony Brook connected by Greenport, Riverhead, Islip, and Montauk is connected to Sag Harbor, and Oriental Point is connected by the Greenport. So map of the Long Island. So electric circuits. In an electric circuit, the junctions are vertices as a component, as an edges. How do you connect those components? The capacity, resistor, maybe component. These components are edges, and these vertices are junctions. Make junctions, vertices are junctions. So other graphs, social network. How's your Facebook graph look like? So from me, I have a couple of you undergraduate students are connected, and they are connected. And graph it keep expanding, right? So how many hops do you need to be connected to Trump? How many hops? 5 or 6, maybe shorter. As we're living in a more and more advanced world, meaning more data-related world, maybe 2-3 hops is enough in a social network, right? And the World Wide Web, www. So how can I connect to the Google? Directly, or Google has multiple CDNs. Okay, so what's the best way to watch the YouTube? What's the best way to watch Netflix? Not just go to the direct Netflix server. I can go to my local Netflix. This concept called the CDN, and this is still the computer networks. Okay, so control flow within the computer program. So if you analyze your computer code, there is a flow chart you can draw, and pairwise the similarity between two items. So we can represent it in a graph. Because if you think about the big companies in today's world, Facebook, Instagram, maybe Google, maybe Apple, Tesla, right? So let's talk about the Facebook. They have a connection, and the value is as much as the Samsung itself. As much as like 5 times more than a Hyundai. They just started. How they do? Because whenever you open the internet, whenever you open the computer or your phone, you access to the Facebook. Then that makes the edges connected to everybody. Okay, so long time ago, if you want to talk to someone, you have to send a letter. Now just click messages by a connection, whoever wants to. Right. Flavor of the graph. The first step in any graph problem is determining which flavor of graph you are dealing with. Learning to talk is important and is an important part of the walking to walk. Okay, so the graph consists of graph. And flavor graph has a big impact on which algorithms are appropriate and efficient. So in directed and undirected graph. Directed, direction. I can go to this way, but I cannot go to this way because it is directed. Something like a road, one-way road in the road network. Okay. So G vertex graph is vertex and edges is undirected. If edge xy, it implies yx. Okay. If xy implies yx, which means you are undirected. If it's directed, it'll never be the same because it is directed. Okay. Road networks between cities are typically undirected because of one-way. In street network within cities are almost always directed because of the one-way street. Most graph and graph theoretic interest are undirected. And weighted and unweighted. In weighted graphs, each edge of a G is assigned to numerical value over weight. Something like my road to from IGC to Yonsei. If there is a heavy traffic, this value should increase if I'm calculating in the view of the time. Right? The edges of the road network graph might be weighted with their length and drive time or speed limit. So in unweighted graph, there is no cost distinction between various edges and vertices. There is no weight concept. Oh, here is a weight concept. So simple and non-simple graph. Certain types of edge complicates within graph. A self-loop. Where does this self-loop happen? So in a friendship graph, are you a friend of your? So are you your own friend? Maybe it is a philosophical problem, philosophical issue. Are you your own friend? No? Okay, so the edge xy is multiple edge if occurs more than once in a graph. So simple graph, the non-simple, complex. I'm my own friend, okay. I may have 2 connections. Even with the same person, I can have 2 connections, is it? How I deal with the friend, how I deal with your friend as a boss of the company, something like this. Any graph which avoids these structure is called simple. And sparse and dense graph. A graph are sparse when only small fraction of these possible numbers of vertices are actually have edges defined between them. And if you have all the edges or most of edges, we call the dense. If it is fully connected, we call the full graph, fully connected graph. So graphs are usually sparse due to the application specific constraint, and road network must be sparse because of road junction. And cyclic and acyclic. Cyclic meaning if I started from here, I can come back to the point. Acyclic meaning if I started from here, I'm not able to come back to this point. Okay. So if the graph creates the cycle, we call the cyclic graph. If the graph does not create the cycle, then we call the acyclic graph. So directed acyclic graphs are called the DAG, directly acyclic graphs. They arise naturally in scheduling problem where directed edge xy indicates x must occur before y. Then, because it is directed, then I can go to there, but y to x is not guaranteed. So embedded and topological graph. Embedded graph is simplified for the meaning. But if you look in the deep inside, it actually looked like this. Road from Seoul, road from IGC to Seoul. The road is very thin, but we are using, okay. So embedded, you kill the detail and only pull the essence of it. So is there a drawing of the graph that matters, as in the road and electrical circuits? For example, TSP, traveling salesperson, or shortest path on a point in the plane. This topological actual graph is not, doesn't mean it. So this graph has some value. Okay, I can simplify it. Grid graph and planar graph. If I do on the grid point to point, I can also do planar all of the places. So let's look at the friendship graph. Consider a graph where the vertices are people. And there is an edge between two people, if and only if they are the friend. So Bill Clinton and Hillary Clinton is a friend. Obama is a friend. Bush is only friend to the Obama. Maybe some friend has no relationship. So graph is well defined on any set of people, Stony Brook and New York of the world. Okay, so in our case, so small computer science, SUNY Korea, IGC, Songdo, and Korea, and keep increasing. So if I am your friend, does it mean you are my friend? Do you think so? So if I am your friend, does that mean you are my friend? So a friend is undirected if xy implies yx. Oh, we understand what it is, meaning undirected. Otherwise, graph is directed. So let's say heard of graph. Heard of graph meaning I know many, I know BTS, but BTS never knows me. None of them never knows me, right? I heard of the BTS, BTS never heard of it. So does it mean I'm friend of the BTS? No, because we are directed. So had conversation with, well, I had a conversation with Kwangmin. Kwangmin and Kwangmin conversation with me. Then it means we had a conversation with, right? Then because conversation require partner. Okay, then in this case, we can call undirected, but this case called directed. So let's say, am I linked by some chain of friendship to a particular celebrity? So let's say your cousin Eugene is a celebrity. Let's say, what's the right name? Let's say Kwangmin is a member of BTS. Kwangmin is not. Yeah. Okay. A path is a sequence of edges connected to vertices. Since Eugene or Kwangmin is my father's sister's husband's son. Okay. There's path between them. Eugene is my father's sister's husband's son. What do we call this? We are cousin, right? So if I were trying to impress you to how tight I am with the Eugene or Kwangmin, a member of BTS, then I'll be much better off to saying that uncle know him than to go into the details how I connected to uncle. So rather than I introduce my cousin, oh, I can say, oh, he's my uncle's son, all right? So I don't say, okay, he's my father's sister's husband, my father's sister's husband's son. We don't use that, okay? So we open interested in shortest path. What's the best representation of between two vertices? Okay, that's what we care. So is there a path of the friends between any two people? So a graph is connected if there is a path between any two vertices. Okay. A directed graph is strongly connected if there is directed path between two vertices. Okay, I can say the term strongly connected if there is a directed path between any two vertices. The notation of the 6th degree of separation presumes the world's social network is connected by graph. Do you understand the 6th graph, what it is? So in the world, we have 7 billion people. So whoever connected to out of 7 billion with the multiple 6 hops, I could be connected. Maybe I could be connected to someone in Sri Lanka, right? Then I'm connected to Stara, and Stara is connected to multiple points. 5 steps. That's the 6 degree separation. That's a very theoretical thing, and it is. I think it received the Nobel Prize. Maybe not. Okay. So, who has the most friend in the view of the Facebook? Who has more than 1,000 friends? Not in here? No? Don't want to be participating in the class? Nope. Okay, so I saw some student has more than 1,000, about 2,000 connection. Yeah, so degree of the vertex means how many direct edges do you have? If you have more degree, meaning you are popular. If you have only 1 degree, you're less popular, right? So what is largest clique? A social clique is a group of mutual friends who all hang around together. So you have your own clique, right? Your friendship go together, and so graph theoretic clique is a complete subgraph where each vertex pair has an edge between them. Okay, so my clique. Okay, within the friendship, we would expect the large clique correspond to the workplace, like a Sunni Korea, and clique of the IGC, clique of the religious organization, clique of school, and clique of the continent, clique of the earth. So let's think about from now. So data structure, I just introduced the concept of the graph, right? So data structure for the graph. What is the best way to represent it? I may use adjacent matrix, or I may use a list, right? So 2 main structures for represent the graph. It could be a matrix or list. So assume graph is vertex and edges, contains n vertices and m edges. So we can represent the G using by m by n matrix. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. So if 1 and 4 are friend, let's say it is directed. If it is directed, means 1 is friend of 4, but 4 is not a friend of 1. If it is undirected, if I am friend of 4, 4 is also friend of 1. Clear? If not, 0. 1 myself is always I am my friend. I am my friend. Okay, so we understand that. Let's talk about undirected. So can we save space if a graph is undirected? What if the graph is sparse? So question is, I make the data representation graph in the matrix. So I want to save the space when it is undirected. How? And
if it's undirected, it means there are two-way connection, right?
Yes. So if the graph is sparse, how can you save the space? Do you understand the question? Right? So let's discuss about it. Let's think about for 1 minute. Janara, I can see you understand the point. Okay. So think about for 2 minutes, and I'm gonna ask you to answer from who has a lower score. Okay, 승재 and PK Taejun and Yura and Kosoyoung. Okay, so I'm gonna ask you about this question. Okay, let's think about for 2 minutes. Okay, ready? 승재?
Sorry, I'm not sure about it.
Okay. Taejun?
My immediate guess is that I think we can save space if the graph is undirected, because you would have I assume that we would have like a less big O notation if the graphs are undirected, so that we can save like unnecessary for example, memory, I guess.
How?
Well, for example, if I think we can minimize it by sort of thinking of it as a like a linked list, I guess, like one directional linked list.
Okay.
So
by using a linked list.
Sort of, yeah.
Sort of. Okay, good point. How about PK? Okay, Yura?
Yes.
Yeah. Any guess?
I guess if the graph is undirect, we can save the space.
How?
Because we can use only the half of the matrix M.
Perfect. Great. So Yura says, okay, since we are using undirected, meaning if I am a friend of 4, 4 is my friend. So if you divide by half, this value will appear this again, and this value appear this again. Then I can eliminate the half space of it, right? Then I can save the space. Perfect. So do you have additional idea? What if the sparse, link is sparse? How can you save it more?
I'm thinking about a relational tree.
Relational tree. What is relational tree?
So first of all, we select all the nodes that are accessible.
Mm.
Like let's say 5 of the nodes are, all of them are accessible. And then we start with with any number. Let's say we start with 1, and then we assign like vertices as links. Like 1 goes to 3 and to 2, and then we continue. So at the end we have like a tree with children and the relations to each other.
So you want to build a tree with the graph.
Yeah.
Okay. Then how can that save the space, or how can they save the energy? So relational graph, relational graph. Let's keep expanding it to all the values. Then how can this one save, and how can this one increase the efficiency?
I guess it will save some time when we want to find a relation between 2 nodes, like if 2 nodes are related or not. Like if you can access another node from this node. But I'm not sure about it yet, but I just want to try to maybe implement it using a tree later.
Good point. Okay, thank you. Anyone else?
I think, hello, my name is Youngjae.
I can see.
And I think if the graph is sparse, then it's not a good idea to use adjacency matrix, because adjacency matrix has space complexity of O(n) squared. So if there's not much number of edges, then like the adjacency matrix will just have like take a lot of space in a computer and just never use. So I think it's better to use a list for like sparse graphs.
Professor, I have another idea.
Okay, one second.
Yeah.
Okay, Youngjae, thank you. Go ahead.
Yeah, I would use hash table from A to for vertices, and just append each element with the breadth first search, and that'll save. And I'll not add the duplicates.
So you want to use hash table? How?
Like listing the vertices and
all vertices.
I'm sorry?
All the vertices in the hash.
Yeah.
In the head of the hash is all vertices.
And append those to the vertices for the breadth first search, and not adding the duplicates on the latter vertices when it's connected.
So you have hash table in there, all the vertices are there, and from there you are adding your degree, your adjacent, your direct neighbors. Is that what you're saying?
Just direct neighbors.
Okay, so how's it different to the list? It just looks like a list, isn't it?
But you can search little bit faster, I think. I'm not sure.
So you try to approach this one a hash, but as you're drawing this, it says just look like list, isn't it?
Oh, how can you represent it as list? I don't have an idea. Like
So,
not a map.
so list is look like this. Okay, who's my next? Who's my next? And who's my next, right? So we always had a list header.
Yeah.
Okay. Every time I have my own vertices, I have my neighbors. Oh, from there. Okay. If you just hook up on the head of it, look like the same.
Oh yeah, that's true.
Yeah. Okay. Good point. All right. Okay. So we can save the when it is undirected by ignore half of it, and if there is a sparse, we can use adjacent list, which is the concept of list. Also look like hash table, what the Seung-Jun says. Okay, so adjacent list consists of n by 1 array of pointer, where ith element points to the linked list and edge incident on the vertices. So this graph is represented to my list. So to test edge is a graph, is in the graph, then I can search only this one. And it takes how many hops and how long does it take? Then I can search through 1 to 5. Is 2 and 5 is connected? Oh, I can say, oh, 2 and 5 is connected. Okay, 3 and 5 is connected. 3, 5, no. Then how much hops do we need? Then what do I need to do? BFS. 3 and go to 2. Oh, with the 2 hops, 3 and 4. Oh, with the 2 hops, with the 2 path. Do you see what I do? So do it again. So I just created an adjacent list. So I just using the graph representation by using the adjacent list. In there, so we know how to convert it, right? 1, 2, 3, 4, 5. I make 1, 2, 3, 4, 5. 1 is connected to 2 and 5. 1 is connected to 2 and 5. 2 is connected to 1, 3, 4, 5. 2 is 1, 5, 3, 4, right? 3 is connected to 2 and 4, 2 and 4. You know what I do, right? Then I can simply do, is that 2 and 5 is connected? Oh, I can say, okay, 2, by searching 5, oh, I can quickly find it. And go to 5, oh, I can quickly find it. Even if it's directed or undirected, I can quickly find it because I only need to search on this. What if 2 and 3 and 5 is connected, direct connected? Oh, go to 3, no. 5, no. Then how many hops do I need to be connected by 3 and 5? It is common when you are doing a transportation or navigation system, we always do this. We are hopping to hops. So we have multiple paths at the joint. So 3, go to 2. From 2, I do BFS. So 2, go to the, with the 1 hop, I can search. And go to 5. And 5, I go to 3. And I can go to 4. Oh, with the 2 hops, I could be connected. Okay. So let's think about this. So trade-off between adjacent list and adjacent matrices. We just saw how we represent our graph into a list or into a matrices. Who's the better? In what computations? So what is faster between two? If we do just check, does it exist? And what is fast? Find the vertices degree. How many edges, how many degrees does it have? That vertex. So less memory on small graph and less memory on the big graph. So edge insertion or deletion, which one is winner? So faster to traverse the graph. So better for most problem. Which one is best? So I have 1, 2, 3, 4, 5, 6, 7. So you can say You can say this, maybe just testing it, then maybe adjacent list. Something like this, some supporting comments if you want to. Let's have a quick quiz on this, 1 through 7. So I'll create the quick quiz on the Google Classroom. Quiz assignment. Which one? I won't use this. Just please delete. So I just create the quick assignment, quick quiz. So answer to this 7 questions, 1 through 7. Which one is more efficient? Good. Okay. Let's close the quiz in 5 minutes. Do you see what we are doing, right? So when we are doing, as we are doing online class without participation, it is not that useful.